My name is Abdullah Almutairi, a graduate student researcher at UC San Diego. First of all, it's a great honor to be here today among you to give a presentation on behalf of Professor Ahmed Elgamal and Dr. Jinshilu about our ongoing project, a systematic computational framework for multi-span bridge PBEE applications. I can go direct to the point. As we all know, the peer PBEE consists of 4 probabilistic models, each with its own uncertainties. We have the hazard models, where we can get the hazard levels, 2%, 10%, and 50% and 50% in 50 years through the demand model. After performing the time history analysis, we can get the engineering demand parameters that are used to trigger specific damage states. Each will come with its corresponding repair methods and repair items that needed to come up with a loss model in terms of repair cost and repair time. By previous effort from Dr. Kevin Mackey, he divided the bridge into a set of structural components, each with its own EDP and corresponding damage states, where the small damage states relate to the low-level damage, and as you can get higher, then the damage will be more severe. For example, we have PG1. The EDP corresponding to that is the maximum column drift ratio. We have the first damage states, the concrete cracking is the low-level damage. As you get higher, then you have the spalling, cover-up spalling, the bar buckling, and the most severe damage is the failure, where we need to replace the column. The previous work by Dr. Jinshilu, we combined the nonlinear time history analysis with the PBEE applications using a software, Bridge PBEE. However, this software is limited to 2-span bridges, single column bent. The good thing about this software is a user interface OpenSees that the soil structure interaction is modeled using 3D soil mesh. Our new software, with the project I'm presenting today, is the MS Bridge. Is the new user interface, OpenSees user interface. It's a computational user interface to combine nonlinear time history analysis, and the OpenSees is employed to perform the nonlinear time history analysis. Using MS Bridge, we can model column, curve, or straight, single column bent, or more than one column per bent. We can conveniently handle the soil structure interaction using the soil springs, PY in the lateral, TZ in the vertical, and QZ for the end bearing. In addition, we can also model the soil structure interaction using foundation matrix by Lam and Martin, where we have a matrix 6 by 6, each element represent a stiffness at a direction. Using MS Bridge, we have different abutment models. We can have the elastic, where we have stiffnesses at each direction, longitudinal, transverse, and vertical. We can have roller, where we have infinitely rigid in the vertical direction and free to move in all other directions. In addition, we can have more complicated abutment model, the seat-type abutment, where we can see the longitudinal gap and the bearing. Using MS Bridge, we can view the motion, see the intensity measures, visualize plastic hinges, and perform mode shape analysis. With that said, I can show to you a demo case of a pushover analysis using MS Bridge. By default, it's rigid. We can change it to soil springs. We have all the models built in the software, the soft clay, the sand reese. We have the corresponding PY curves. I chose the push-over analysis. It's fast and easy to perform in order to see the results. You can display the output, the default mesh. You can play animation, control the speed. You can display either the column above the ground or below the ground for the pile, profile, or time history. So this is the first stage of this combination, the nonlinear time history analysis. If you want to show as quick demo case of the PBEE output, I have this video that shows that. After performing the time history analysis, we can show the EDPs. We have 11 as defined by Dr. Kevin Mackey. We can see different columns. We can also control the intensity measure. For this example, we have PGV. So with the new version of MS Bridge, the user can update all the performance metrics. So all these parameters can be changed by the user without going to the code, directly from the user interface. With that, you can show the repair cost, the loss model, by performance group, the total, disaggregated by repair quantity, and the contribution to the standard deviation. In addition, you can define the probability of exceedance at specific location to calculate the hazard curves. In the mean annual frequency, you can specify an intensity measure to see the disaggregation to perform kind of sensitivity analysis or something like that. Using MS Bridge, we modeled real case bridges, Coronado Bridge in San Diego, and Eureka Channel Bridge in Northern California. I can go very quick in a case study. We have this case study, a single column, a straight box girder reinforced concrete, 5 span, known as Type 11 in Ketchum et al. 2004. You can see seat type abutment, box girder, and circular column. Here we have the FE modeling, the column cross section, the fiber section, the stress-strain relationship for the core concrete, cover concrete, steel, and moment curvature. All can be done using the user interface. Similar to the video, I can go very quickly on that. This is the EDP, the loss model in terms of repair cost. So this is disaggregated by performance group, the 11 performance group, or the total normalized, so repair cost ratio. In addition, we have the loss model in terms of repair time, disaggregated by repair items. The hazard curves, mean annual frequency of the repair cost ratio, or mean annual frequency in terms of the repair time. And also, again, the disaggregation at specific intensity measure. I chose 100 PGV, centimeter per second, PGV. So you can see all the disaggregation of the performance group. Similar can be done to the repair items. In order to verify that MS Bridge is working fine, we used one of the published case study by Dr. Kevin Mackey, and this is the one we chose. You can see the publications in the SDEE journal. So here on this simple case, 2-span single column. For the rigid case, he got around 34% repair cost ratio. We got the same. And the repair cost will start accumulating at 40 PGV. We got a very good match. After showing a case study, a simple typical in California, we can now perform the PBEE into a real case, large, retrofitted, highly instrumented bridge, Samoa Channel Bridge, a 20 span, in Northern California, 764 meter long and 10.4 meter wide. You can see the topography and the elevation view of the bridge. We have the column cross section, the pile group, the mud line, and this cross section is for the S8, which is this guy. However, when we modeled the Samoa Channel Bridge and MS Bridge, we calibrated the model based on the actual bridge response by a publication from Wang et al. 2018, Ning Wang, former student with Professor Ahmed Elgamal. We found that the foundation stiffness at the pile cap level reduces as the amplitude increases. And in order to model this and calibrate it to our input file, we use nonlinear material that capture this kind of reduction. It's worth mentioning here that the stiffness reduction between S5 and S12 is due to the free span. You can see it here. So we have calibrated the model based on the data we have, and we performed the time history analysis and PBEE. We are still working on this paper. We're going to apply more ground motions, study it more. We have the 3 hazard levels, and similar to the typical bridge where we have kind of symmetry, both abutment at left and right were triggered at the same damage state. However, for this kind of bridge, they are not. And we can also see that the foundation, we start to see the effect of the foundation, which is the very last performance group, PG11. In addition to the repair cost and repair time, we believe that this methodology can be extended to also include some sustainability metric to the PBEE. So now we include the repair carbon footprint. We got these economic input-output multipliers from the publication from Dr. Kevin Mackey. Professor Ahmed Elgamal was included in that. We got the corresponding multipliers, and we got the results in terms of the carbon footprint of repair. Additional development is not part of this project, but we are working on. If you want to perform liquefaction-induced lateral spreading into this kind of analysis, also using MS Bridge, it's the same analysis, can be found in Ledesma and Bray, 2008, and Professor Bray is here today. So we can apply the displacement, impose displacement along the pile height to represent the soil movement after liquefaction. We believe that MS Bridge can be used specifically, and PBEE in general, not only to bridges, but also to other kind of structures. Professor Elgamal has shown very high interest in adding this methodology to other structure, and now we are working on pile-supported walls, very well-known, common in the US ports, so we can use it, apply it, analyze it, and study the performance assessment. And I used the model found in Su et al. 2017. With that said, we have the summary. MS Bridge is easy to use software, conveniently handling soil structure interaction, performing nonlinear time history analysis, automatic linking to performance groups and generation of PBEE quantities, enabling tool for research if you want to do sensitivity analysis, what-if scenarios, incorporating the latest research outcomes from other related peer. For example, if you have a new kind of models, abutment models or what's not, you can simply add it. we are studying the effectiveness of different design options. For example, if you have a retrofit, then you can study both before and after and see the effectiveness of having a specific kind of retrofit. Finally, we are supporting the green design by including the carbon footprint of repair as a performance measure. Thank you.
Thank you, Abdullah. This is very interesting. I have a quick question. So when you did this Eureka bridge case and you did that calibration, and then you mentioned here sensitivity, is that done in a trial and error basis, or there are features in bridge PBE to do that?
We added this feature to the MS bridge. However, it's eventually a trial and error. So we are changing one metric, see the effect, and keep on doing this. With the new MS bridge, it's only a click of a button to choose which item you need to vary, give all the different values. It can do this for you.
I'm also going to mention something about Professor Derkurigan again, sorry. Many years ago, there was the sensitivity toolbox in OpenSeas using direct differentiation. Are you familiar with that? Is that something that can help with bridge PBEE and to do this sensitivity study more? Are you familiar with that? I don't know.
Yeah, we know about this, but we want to do it in a very simple, straightforward way. So we are doing it straight and actually just changing. And the good thing about this software that it's independent of the time history analysis. Once it's done, then you can play with the methodology as you want. Then it's actually trial and error. I believe that it's a very good addition to include. We discussed before with Professor Ahmed Elgamal about this, but we thought that let's keep it simple and have something ready to be presented and used by the users.
Any conflict?
Michael Scott here has done a lot of work implementing sensitivities, right, Michael?
Yes.
Is that says?
Yes.
Is there any new development happened since the work of Teria Hawkins?
Yeah, Teria started it in the early versions of OpenSeas, and then Scott improved the implementation. I don't know what the state of it is, but right now, at one time it was working. The problem with not doing it in terms of direct differentiation, which is sort of it's like finite element, and doing it by finite difference, is that you could get very wrong results, because by finite difference you perturb a parameter. And if you're doing nonlinear analysis has convergence criteria, and your perturbation of the parameter and the resulting perturbation of the response, they may not correspond. Some of the perturbation in the response could be because of your convergence criteria in the nonlinear analysis. So it's very problematic. If you make a very small change in the parameter, all of the change in the response could be due to your convergence criteria. So
This is
doing a
correct.
finite difference is very tricky. And
Many of these parameters are also,
Pardon?
many of these parameters are not independent. So
Yeah.
there's a lot of dependencies. So how you change something here, it's not just they are correlated.
This is true actually. If you want to change any column properties or something with the bridge and perform the nonlinear time history analysis again, then yeah, it's a complete different story. What we are doing in the sensitivity analysis, we're only changing the performance parameters. So for example, a unit cost of an item, or maybe a damage state's value, or something like that. So this kind of sensitivity analysis that we are doing. But yeah, this is true. If you want to change something with the actual input file, then it's another story. So you have to run everything again. It's a different example.
what you're referring to is a parameter estimation problem, and I think for the nonlinear problems, you can use like uncentered common filters to estimate properties of these theoretic models. But then again, it becomes almost intractable if you have many multiple nonlinearities competing. So you first have to isolate the nonlinearity and then reduce the parameters by doing some smart sampling and then apply a Kalman filter or something like that. I mean, that's also one of the things that's kind of lacking in the OpenC's arsenal or peer arsenal, which is what do you do with these sophisticated parameter estimation problems? You can
Frank
either
said there would be
calibration of a
artificial
constituent
intelligence
model,
added. So.
yeah, or
That was
extracting the field properties for a liquefaction model from a downhole array. All of these are nonlinear parameter estimation problems.
Yeah, but certainly an effort like this that make all this graphical user interface and having all these features at least encourages people to explore these intractable problems, make it a little bit manageable. May not come up with a solution, but at least to make engineers in Caltrans willing to consider using PBEE and make it more friendly for them. Any other comments on Abdullah? I'm using the time for the discussion also. So.
I have to acknowledge Dr. Junchilu. He did most of the difficult parts. I was part of it. I was trying to help in coding and what's not, but he did more than 50% of everything. So he should take all the credit.
Thank you.
So I have a few questions. First of all, does the program create its own input file to be fed into OpenSeas? Or can it read on each? Let's say you create a model manually using tickle files and then you run the model, or just feed the program the tickle files. Can it generate a...
Can do both.
Or it can do both?
It can do both.
That's nice.
It's a good point that you mentioned, Ahmed. If you see the column cross-section, actually we don't have a click of a button where you can define this kind of cross-section along with the discretization. So you have to write a tickle file with all, the properties and discretizations and this kind of geometry. So this is what we did. We wrote the tickle file. We fed it to the MS bridge, and they understand the performance. We verified it, and then we can have it. In addition, if you have just like the case study, the first one, the typical bridge, when you have audio circular, then you don't have to do this. You can do it. You still can do it, and MS bridge can understand it. But we have this feature that you can only define the diameter and number of bars and what's not. Then he can do it for you.
So does that, how does it do that? I mean, does it actually parse the tickle file? Or
Yes.
does it do something else?
Maybe in the video it will be, it was part of
So
that.
let's say I create a model of maybe a building, and I have multiple tickle files. Can I just tell the program, okay, this is the file I will start running the model with? Can it go through each of the files or no?
I mean, if you have a specific component, then yeah, you can feed it the tickle file.
Oh,
But you have everything from scratch. Whenever you have this input file and you run it, you can see all the files. You can get to any file and change it according to your knowledge to OpenSeas. You can do that, but something from scratch, and especially not a bridge, no, it's not working like this. Yeah, it needs more work to.
Okay.
Yeah, it's
One
way
question I
beyond
have
our
is,
scope.
how big a model can it display? I mean, I have tried rendering my own 3D OpenSeas models, and with, let's say, more than 3 or maybe more than 1,000 nodes, especially in MATLAB, it becomes super slow if it's in 3 dimensions.
It is slow. It is slow.
Okay.
Yeah, that's why I showed only the pushover. If you want to do the time history, then.
No, I mean,
okay,
I
I'll
don't mean
come
the
back tomorrow.
analysis. I don't mean the analysis. I mean just the rendering itself.
Is
No,
he
you
using
display,
MATLAB
yeah,
for
you
this?
still can display. Yeah, you can display.
Are you using MATLAB for this the interface or something else?
No, we're using the OpenSeas directly.
No, I'm saying for the interface, for the graphical user interface. What kind of tools are you using?
I think
You can answer. Go ahead.
Yeah, it's using C#.
Oh, okay.
C# and for Windows WPF, Windows Presentation Framework.
for bridge PBEE we were using C++.
C#.
For MS Bridge, we use C Sharp.
Yeah, so much faster than MATLAB.
So one last one, more of a comment. Have you considered looking into the JSON print that Frank and all the others are adding into OpenSeas? Because that gives a very organized output format, which I believe you can actually parse back. You might want to look into that.
Unfortunately, we did not.
Mhm.
But based on what I have seen so far today, I'll go back to UC San Diego with a great idea to further improve the software.
Okay, thank you very much.
Thank you.